Hello? Hello?
Hello.
Good morning, everyone.
Good morning.
So today we're gonna look at some questions. And we're gonna start with the questions regarding the domain. So let's look at this function. F of x equals square root of 5x minus 6. Well, we need to find the domain for a square root function. So firstly, I wanna introduce the definition for a radical, okay? This is a radical, all right? This is a radical. And in this radical expression, there are three parts. N here is called the index. It has another name, it's called a root number. When you see the root number is absent, that means the radical is a square root. So if we are going to have a square root, you normally do not see the second. You do not see the index 2 over there, okay? But if n is 3, then the radical is a cube root. So this is a, for example, this is square root of x. We don't really write the 2 out. Yeah, most of the time we just do not write it out. It's defaulted as 2, square root. If the n is 3, then that is a cube root, right? If n is 4, that is the fourth root, and so on and so on. So that's the first part in radical is called a root number or index. And this symbol is the radical symbol. When you see that, that means we are having a radical. The third part is the entire expression under the radical symbol. In this case, I use a star to represent the entire expression under the radical symbol, and we call that radicand. Is that important to remember those names? I think it will help if you know the names, okay? So I would recommend you know this name, radicand. When I say radicand of a radical, I mean the entire thing under the radical symbol, okay? Radicand. So very important. If we have a radical function and then the index is even, if the index is even, then we require the radicand non-negative, okay? Yeah, because we are looking at the function in the real number set, real number set. So for example, a square root of -5. We all know this is not a real number, right? This is not real number. So if the index is 2, which is even number, right? Or 4, or 6, or 8, yeah. If the index is even number, then the radicand has to be non-negative. Okay, cannot be negative because if it's a negative, it's undefined. It's not a real number. Okay, but if the index is odd number, we don't really have any restriction on the radicand. We do not have the restriction on the radicand. The radicand could be negative, it's totally fine. For example, cube root of -1 is just a -1, right? Cube root of -8 is -2. So cube root, when the index is odd, is an odd number, we do not have any restrictions on the radicand. Here, I want to emphasize, if the index of a radical function is even number, then the radicand has to be non-negative. Okay, specifically, most of the time we don't really have to worry about fourth through or sixth through. We only do like a second, like when index number is 2, square root, or maybe occasionally cube root, right? So in this case, our function is a square root function, yeah, because the defaulted index here is 2. Okay, we have a square root. Yeah, square root index is 2, even number. So the radicand, what is radicand? The entire thing under the radical symbol. In this case, the radicand is 5x minus 6. It's not just x, okay? It's the entire thing under the radical. The radicand of a square root has to be non-negative. In other words, bigger than or equal to 0, okay? All right, so we are going to solve to find the domain of the function. We need to solve this inequality. 5x minus 6 bigger than or equal to 0. And the solution set of that inequality is the domain of the function. All right, let's solve it. We can add a 6 to each side. 6 and negative cancel. We have 5x bigger than or equal to 6. And then divide each side by 5. 5 over 5 is 1, so x is bigger than or equal to 6 over 5. Or you can say 6 over 5 is 1.2, right, as decimal. But I'd like to keep the result as a fraction if it's simplified. So the domain of the function f of x is any real numbers no less than 6 over 5. Okay? Yeah, if we draw the real number line, this is 6 over 5. Yeah, any number bigger than or equal to. Bigger than or equal to, no less than, right? Bigger than or equal to. So bigger than or at. Yeah. So that's the domain. As an interval, the domain is from 6 over 5 to infinity, right? As you can see, this piece has the left endpoint 6 over 5, right endpoint is positive infinity. We're going to have a bracket, left-handed bracket to frame 6 over 5 because the 6 over 5 itself is in the domain, okay? And of course, we always use parentheses to frame infinity, all right? So this is how do we find the domain for a radical function. Let me summarize. When we need to find the domain for a radical function, first thing, look at the index. The index. If the index is an odd number, like 3, we don't have to worry about it. There's no restriction. Yeah, very likely it's all real. Of course, we have to look at what function exactly look like, right? But if the index is 2, is an even number, then you have to write down the radicand, which is the entire thing under the radical, and make it bigger than or equal to 0. And you're going to solve that inequality. The solution set is going to be the domain of the function. Okay, so let me know if I'm clear. Whatever I covered today, whatever the questions I covered today, you need to pay very attention because they are very closely related to the upcoming exam 1. Okay? Any questions? Normally for the virtual meeting, yeah, I pause like 3 seconds. If nobody responds, I'll just keep moving to the next question. All right. All right. So the next question, function h, is a rational. Okay, when we go to unit 3, you would know clearly what is a rational function. This specific function, y equals 1 over x, is a rational function, but you don't have to know that at this point. But you need to know that function is the famous reciprocal function. This is the reciprocal function. The name makes perfect sense because the output of the function is always equal to the reciprocal of the input function because the y equals 1 over x, right? Yeah, so this is the reciprocal function. I need you to know the graph of the reciprocal function. I need you to know the graph of the reciprocal function. You should see that in the activity, last week. What does the graph of the reciprocal function look like? It has 2 branches, okay? It passes 1, 1 and negative 1, negative 1. In quadrant 1, it has a branch. In quadrant 2, it has another branch. Quadrant 3, it has another branch. You would say, how am I supposed to know the graph look like this? So if you have a simple function, very basic function, and you want to know the graph of the function, besides using your graphing calculator, you can also make a table and find some convenient numbers. For example, in this case, I draw a 2-column table, right? I'm going to start from -3, and then do -2, -1. Zero doesn't work here. As you can see, if let's say we write 0 here, okay? We'll see later. And then 1, 2, 3. So when x equals -3, y is the reciprocal, so it's 1 over -1 over 3, right? When x equals -2, y is -½ When x equals -1, y is the reciprocal of -1, which is also -1. When x equals 0, the reciprocal of 0 is undefined, does not exist. Okay, DNE does not exist. Okay, if you use your calculator to divide 1 by 0, you would have an error. Okay, yeah. So that means we don't have x equals 0. Means that x does not assume the value of 0. 0 is not. Okay, 0 is not in the domain. Very important. When x equals 1, y is the reciprocal of 1. When x equals 2, y is half. When x equals 3, y is 1/3. And what do? You're gonna draw some, plot those 6 points, right? -3, comma, -1/3, -2, comma, -1/2, -1, comma, -1, right? Yeah. So you can find more points. Yeah, I only found a few here. And in quadrant 1, when x equals 1 is 1, right? And then 2, comma, half, 3, comma, 1/3. Yeah, you can put more points to make your the shape of the graph better to you. All right. So, but also from making the table, you would notice x could assume any numbers except 0. Okay, x could assume -1/2, -1/3, or negative, very tiny negative number, right? Yeah, any real number x could assume except 0. So the domain of the function is all real except 0. So how do we write the domain? The domain of the reciprocal function f of x equals 1 over x is all real except 0. Okay, and let's draw the real number line. Let's say 0 is here. Any real number except 0. Okay, we have to exclude the 0 from the real number line. Any other number is fine. Numbers to the left of 0, numbers to the right of 0. Well, here, the region covered by the red color is not one interval, it's 2 intervals. Okay, because if we use our pen to trace the red region, we have to stop at the 0. We are not able to just trace the entire domain without lifting our pen, right? So this is not one interval. The domain of the reciprocal function has 2 intervals. How do we do that? How do we use the interval notation to represent the domain for the reciprocal function? We're going to look at the 2 pieces separately. The first piece from -infinity to 0, open, okay, because 0 is excluded. The second piece from 0 to +infinity, right? And then we're going to use union notation symbol to put them together. That's the way to do it, okay? That's the way to do it. That's the domain. Range is the same thing, okay? Range is the same thing because the output is always equals 1 over the input. Yeah, the numerator is 1, so that means as the quotient y cannot be 0. You can try. You can see. If you put more points in the table, you'll see that. So the range is the same thing, all real except 0. So the range is also, this is a domain, The range is also from net infinity to 0, union 0 to past infinity. We see this problem in the activity last week, right? Yeah, that's how do we find and understand the domain and range for the reciprocal function. Okay, here I have a question just to see if you are following. What if I give you a function f of x equals 1 over x minus 1? I modify the function a little bit. Okay, let's look at this function. What if we have a function f of x equals 1 over x minus 1? What is the domain? Yeah, what is the domain? Let's do domain first. Just want to see if you are there. What's the domain? But let's see who's in the meeting. We're missing 3 students, right? You can unmute yourself, I believe. Unmute yourself and answer the question. Okay. Nobody answer? How about this? So when you need to find a domain for a function who has the variable x in the denominator, this is what you do. You are going to write down the denominator and then make the denominator not equal to 0. Okay? In this case, the denominator is x minus 1. Make it not equal to 0. We all know denominator cannot be 0, right? If the denominator cannot be 0, x minus 1 cannot be 0, then x cannot be 1. So the domain of this function is all real except 1. In the real number line, we're going to exclude 1 from the real number line. And the interval notation for the domain is going to be net infinity to 1, open union 1 to past infinity. All right? Okay, let me give you one more. Just make sure that you understand what I'm talking about. What if you have a function f of x equals 2x plus 1? Same thing, okay? You have variable x in the denominator. If you see a function like that, what you need to do in order to find the domain is you write down the denominator. Write down the denominator. We all know the denominator cannot be 0. Denominator cannot be 0, right? And you solve this inequality. This is also an inequality. -1, so 2x cannot be -1. X cannot be -half. So the domain of this function is all real except -half. All real except -half. So we are going to exclude -half from the real number line. So the domain is union of 2 pieces. Net infinity to -half, open, open, union -half to past infinity. All right? Any responses? Does that make any sense?
Yeah, it does.
Yeah, that makes sense.
Okay. All right. Thank you.
Makes sense.
All right. So that's what are we gonna cover today. What do we cover today about domain? Okay, finding domain. Now we're gonna move to next question. This question is about composite function. All right. I don't know if you start studying this section. Yeah, composite function. I hope you still remember in a class, I like, there are multiple ways to describe a function, but I like to describe a function as a machine. This is my machine. Remember that? Yeah. Whenever you give the machine an input, the machine will produce exactly one corresponding output, right? Yeah. That is a function. Then what is a composite function? Since the composite functions we see at this pre-calc class only involve two functions. So a composite function is an ensemble line. With two machines. All right? Yeah. So what does a composite function look like? It look like this. Or this. It depends on the notation for the two functions. Yeah, it has a circle. Okay, has a circle. All right, this is what you do. When you see the notation f circle g of x, the very first thing to do is to rewrite the notation as f of g of x. Okay, very first thing to do. When you see g circle f of x, you firstly need to know, oh, that is a composite function, right? But I do not like that notation. The professor said, when you see that notation, rewrite it right away. Write it as g parentheses f of x, all right? So f of g of x, this is a composite function. It has the inside function g, outside function f. Okay, outside function is f. Why? Because g is closer to the input. The input is still x. Yeah, the input is in the parenthesis here. X is the input. Because g is closer, we call g the inside function. Whichever the function closer to the input, that's the inside function. Then f further away, a little bit further away, that's the outside function. Okay. Then this composite function can be described as an assembly line. Has two machines. What happened is the input go through the inside function first. Okay. The input x go through the inside function first, and you have a semi-product, kind of like a semi-product, which is, let's say u, okay? U here is g of x. And then the semi-product go inside the outside function. And then the finite product is y. So a composite function with inside function g, outside function f is an assembly line. Yeah. I'm not sure my pronunciation is very standard for this word, but I wrote it down, okay? This is what I'm trying to say. Two machines in it, okay? What if the composite function is g circle f x? Then firstly, rewrite it as g of f of x, right? And this time you know, oh, the inside function is f because f is closer to the input. Yeah, inside function is f. Outside function is g this time. Then this assembly line, two machine. The first machine is going to be f. Yeah, x gonna input gonna go through f first, and then outside function g. So input go through function f, you would have a semi-product, and then go through the outside function, we have the final product. The final product is the output of the composite function. Yeah. I think I might be a little bit too fast, but you know, we have a problem to go through. So once we start to do the problem, you would understand it better, okay? Let's look at this problem. Use the graphs to evaluate the expressions below. Okay, let's see what's this graph. Two graphs, actually, right? On the left, we have the graph for f of x. On the right, we have the graph for g of x. And since both of the two graphs pass the vertical line test, we do have two functions here. Okay, this is function f, is graph, is function g is graph. And let's look at the notation. We need to find the value for f of g of 2. What does that mean? This notation means the output, this notation means the output of the composite function f of g of x when the input is 2. The input is in the parentheses. The inner layer parentheses. So this notation represents the output of this composite function when the input is 2. Are you able to see? We are looking at this here, okay, yellow. We are looking at that function. Are you able to see which function is inside, which function is outside? In the unassembly line, which function, which machine go first, which machine go after? So since g closer to 2, 2 gonna go inside g first, all right? And then go through f. All right, so on your scratch paper, you're gonna draw these 2 machines. Inside machine first, which is g, and the outside function machine f. The input 2. Let's see, when you put a 2 in the machine g, what gonna come out? What would happen after the machine g? Then that's gonna be g of 2, right? Since we're looking at
0.
How do you get a 0?
Because the g of x who put 2 in go to right, and then it's
exactly.
at 0.
Exactly. So since we are looking at machine g, we are looking at the graph g of x on the right? So when x equals 2, look at this black point. This black point is on a curve, and its x coordinate is 2, y coordinate is 0. Okay, so that means when the input of g is 2, the output is 0, right? I hope you see it, everyone. Very good. So now that means the semi-product is 0. The semi-product is 0, and 0 gonna go through f. Also means we're done with g. Well, now we're gonna look at the f. So the 0, so 0 here is going to be the input for f. So you're gonna look at the function on the left. We're done with g. Okay, which point has x value 0? Which point has x value 0?
Be 0, 1.
Exactly. This point is on the curve, right? And the coordinates of the point is 0, 1. X is 0, y is 1. That means for the machine f, when the input is 0, corresponding output is 1. Exactly. This means the machine f produce output 1 when you give it the input 0. There we go. So the answer is 1. Answer is 1. That's it. Is that doable? Composite function, just with 2 functions in it, inside function, outside function. It's just an unassembly line with 2 machines, connect to each other. All right. Let me erase those, and then we're gonna move to the next question. The same problem. Next question. I'd like you to try a little bit, to think for yourself first. Now we are looking at this one, g of f of 0. How are you gonna draw your machines? How are you gonna draw your machines? Which machine first? Which machine?
F first, then g.
First is g. First machine has to be inside function.
First one's f. Second one is g.
Because f is closer to 0, right? 0 is the input. 0 is the input. 0 gonna go through function f, and then go through function g. Let's see. After 0 go inside function f, what's the output? What's gonna be here? What is the semi-product?
That'd be 1.
Okay.
So it'd be, your point is 0, 1.
Yeah, we had that earlier exactly, right? 0, 1. When x is 0, y is 1. Yeah, that means when you give machine F 0, it produce 1 for you. So the finite semi-product is 1. And then 1 gonna go through G. Gonna go through G. 1 gonna go through G. All right?
And the
That means we need to find a point on G whose x coordinate is 1.
output's going to be 1, 5 per coordinate.
Exactly. 1, 5. X is 1, y is 5. So when the input is 1, the output is 5. Done. Okay, I hope it's doable for you. Yeah, some of you, I guess, is already grasp it. And let's do more. If you know this, I don't worry about you would have the point for the exam. Okay, next one, the yellow. This time, f of 1. Yeah, what does that mean? No G, just f. Is that even okay? Can we compose the same function twice? Why not? Totally, okay? It doesn't really discriminate anything. Yeah, the inside function, the outside function could be the same function, no problem. So how are you gonna draw your unexamined lines? F of 1. Obviously, 1 is the input, right? What's the inside function? What's the outside function? It might be a little bit weird for some of you. What's the inside function?
They're both F.
Yeah, both F, exactly. Exactly, very good. Then we just look at the F without it, just do not worry about G, right? Just focus on F. All right, so we need to know the semi-product. What's the output of F when the input is 1? Yeah, we need to find a point on the graph since we're given a graph instead of an equation for F. Which point on F has x coordinate 1? Do you
Will
see the
be,
point?
1,
1,
2
2.
coordinate.
Very good. 1, 2. When x is 1, y is 2. Very good. So when the input is 1, the output of a machine F is 2. Okay. So now we have the semi-product. Okay. The semi-product gonna go through F again. So we want to know when the input is 2, what F gonna produce correspondingly.
0.
Say again?
0.
0, exactly. Yeah, perfect. Yeah, look at this point, 2, 0. That means when x equals 2, y is 0. That means for machine F, when you give the input 2, the corresponding output is 0. And done. All right? Not that very difficult or complicated. Once you understand the idea, it's just so doable. Just two machines together. All right? Let me erase that, and then we move to the last part of this question.
Is there a limit to how many functions you can have together?
Oh, that's a good question. For us, all the composite function only has 2 functions, inside, outside. But technically, you can do many. Let's say f1 of f2 of f3 of f4. You can use many, as many as you want. Like x, here I have 4. Then this is a very long unexamined line, right? Yeah, the inside function is f4, and f3, and f2, and f1, right? Yeah, but we don't see this complicated function. When you, in the future, if you go to calculus class, I think most of the time is 2 functions in a line, sometimes 3, rarely has 4. But for us, the questions on in the homework and the test, only 2 functions. Thank you for the question. Yeah, you can get many. Yeah, function could be very complicated. All right, last one. Let me erase this yellow. and our focus, the last part. Okay, look at the notation. Notation is also very important, okay? G of 5. No F. How do we draw the line for this one? What's the inside function? What's outside function? What's input? Both
G and G.
Yeah, both are G. Input is 5. Very good. So that means this time we do not need to look at F. We only need to look at the G, right? Okay. So the first step, we want to know what's the product, semi product, right? After we put the input in the machine, input is 5. So we're gonna look at the 5 on the x-axis. Okay, this is a 5 on the x-axis, and then trace top and this point. This point has a y value of 4. Do you see it?
Yeah.
Yeah. So that means when the input is a 5, output is a 4. So our semi product is a 4. Okay, half done. And now you're gonna look at when you put a 4 in the machine G, what's gonna be produced, right? And you look at the 4 here, and you go up, 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 this point, right? And you go over, you will see what's the y coordinate. Yeah. And that point, this big black point, has x coordinate 4, y coordinate what? 3, right? That means when the input is 4, output is 3. Done. Do you think you can do that?
Yeah.
You can get this problem correctly if this problem shows on the Unit 1 exam. You the better, okay? Yeah, this is not something very complicated or very difficult. It's just look at the input output, you know. Yeah, it's very doable, very, very doable. Yeah. All right, so through this problem, I think you understand the idea about composite function. All right. Next. Okay, next. This one, we don't have graphs, but we have the function given as an equation. Yeah, function given as equations. Sometimes they give you table. Sometimes they give you graphs, like earlier. Sometimes, like this problem, they give you the function as an equation. Yeah, this is also very important. Let's look at the notation, okay? Find, they use bracket. I wouldn't use a bracket. I use a parenthesis. F of G of X. Yeah, this is what are we looking for? We are looking for F of G of X. We're looking for this composite function. Okay? Inside function G, because it's closer to X. Outside function F, because it's a little bit further away. Both F and G are given as equation, right? Yeah, as we can see, the inside function G is a linear function, is a straight line. The outside function F is a quadratic function, is a parabola. Yeah, but we want to know, after we compose the two functions together with G, and we put the two machines together. G first, G inside, F outside, right? How the output depends on the input. We want to know, we want to find that equation that connects the output of the composite function with the input. Okay? Yeah. This one is different from the previous problem because the previous problem give you the specific value for the input. This time we don't have the specific value for X, right? It's just X. Okay, let me show you how do we process this type of problem. F of G of X. By the way, there are multiple different methods to find the composite function. In the class, we are going to only look at one method. Okay, I'd like you just use that one method. Okay, what method? Get rid of the inside function first. Yeah, this method get rid of the inside function first. What's the inside function? I'm going to use a different color, okay? The inside function is G of X. Yeah, I'm going to replace G of X with x minus 2. Can I? Why not? Like, can you replace a $10 bill with two $5 bill? Yes, because they're the same thing, right? Yeah. Here, we are given g of x is x minus 2. So, of course, we are able to replace g of x with x minus 2, right? After that, we're done with g. Good news is that after that, we're done with g. So this method, we start with the inside function. And now we only need to look at the outside function. Okay, let's look at the outside function. Outside function f of x is a quadratic function, x squared plus 3x. What does this equation tells us? This equation tells us when the input of the function is x, the output is square of x plus triple of x, right? That means the output, of the function always equal to square of input plus triple of input. All right? Yeah, you can rewrite it. Every time you rewrite it, actually helps you to think. Oh, for the function f, the output is always equal to square of input plus triple of input. What if the input is blue? Okay, then the output would be square of blue plus triple of blue. Okay, that would help us to figure out how to write f of x minus 2, how to find f of x minus 2, right? f of blue, yeah, the output of the function f when the input is blue would be equal to blue square plus triple of blue. Blue square plus triple of blue. Oh, what is blue? Blue is x minus 2. And then you probably can just leave it like that. Or if you want to, sometimes the question tell you, sometimes simplify your answer. Okay, since it says simplify your answer, I'm going to simplify it. So I'm gonna use this formula. Remember, we have that in the formula book. A plus b to the power 2 equals a squared plus 2ab plus b squared. It's very fast. If you don't know that formula, you would have to FOIL. It just take a little bit more time, right? Yeah, but it's okay if you really need a FOIL. So I can apply this formula to expand the square of x minus 2. It's going to be x squared minus 4x plus 4. Okay? And then I'm going to apply the distributive property to remove the second parenthesis, 3 times x, 3 times -2, -6. And then I'm going to see if I have any like terms to combine. -4x, positive 3x, negative x, 4 minus 6, -2. All right, this is your formula. Okay, this is your formula for the composite function f of g of x. That is your answer. And I want to remind you, when you take the exam, which is gonna come soon, okay? When you take the exam, it's gonna be the same with when you do your assignments. It's important to read the question carefully. Yeah, for example, sometimes they say, write the equation, yeah, and they already give you y, they already give you equal. Then you don't have to write it again. If you write this again, the market is wrong. Even your answer actually is correct, right? Same with if they have this. Oh, they already give you f of x equals, then you only need to enter the right side of the function, right? But if you are not careful, you don't know, you write this again, that is wrong. And sometimes they require you to enter the entire function. You have to write the whole thing. Then you have to do what it asks you to do, okay? Those details matter. I do not override if you make that. I would not override that mistake if you make that mistake, because they clearly states what to do, what to enter in the cell, right? You have to listen. Very important. when you get a job in the future, and some of you probably already have a job, when your supervisor tells you something clearly, shouldn't you pay attention and just do what the supervisor asks you to do, right? It's very important. Yeah. If you don't pay attention, you make a mistake, then that's a mistake. Okay, I'm not gonna override that. So now we have f of g of x found. All right, so that's how do we find this function. To expand this problem a little bit more, what if they want you to find g circle of f of x? Would you able to find it? Try that yourself, okay? What's the difference? What if the problem is g circle f of x? What's that difference? That means the inside function is f, right? Yeah, inside function is f. Now leave this for you to practice. Yeah, you can do that now to see if you can get it done. F is x squared plus 3x. Yeah, I'm gonna erase those blue just in case it does confuse you. We can try pink this time.
Should we give you the answer?
Should they give you the answer? F? Yeah, f is x squared plus 3x. So we can replace f of x with x squared plus 3x, right?
Yeah.
Yeah. And then we have g. Yeah, this is g. The output of g is very simple. Is 2 less than the input. 2 less than the input.
So it's gonna be 2x squared plus 3x minus 2.
Exactly. Yeah, pink is the input. Input minus 2. Pink is x squared plus 3x. To be honest, this specific part is from unit 1. Yeah, the definition for a function. Input-output correspondence for a function. All right, very good. I think if you are very clear about those two problems, you're pretty good for this section. Yeah, composite function. A lot of times they give you a table or a graph, doesn't matter, and they ask you to find the value of that composite function for a specific input, like the first problem. And this is how you get it done. Okay, draw the line, draw the unsummed line. Sometimes they ask you to find the formula or equation for the composite function. The input is not a specific value, it's just the variable x. And you use this strategy, okay? You get rid of the input function first. All right, so that is the section. So 1.4 is domain and range. No, 1.4 is a straight line. Domain and range 1.3. And 1.5 is composite function. 1.6 is a transformation. Okay, now we're going to talk about transformation. Just in case some of you didn't pay attention when I mentioned that before, so I'm going to show you something very important, okay? This is our Blackboard course shell. There is a there are some folders on the top of the shell. Unit 1 homework assignments, Unit 1 homework answer key, Unit 2, Unit 3, and Unit 4. I'll have Unit 4 ready this week, right? Yeah, Unit 1, you click on it, you have the detailed explanation for each single question in your homework assignments. And I strongly recommend you study those PowerPoint Okay, you study those problems. Just in case some of you don't know, those exist, so I pointed out. All right, transformation. We're gonna learn how many transformations? 10. If we talk about the 10 transformations of a function in detail, the rest of the time of today is not gonna be enough. So to make it a very efficient, you're gonna mainly look at those 10 transformations yourself, okay? Yeah, what are the 10 transformations? Shift a function up, down, right, left, flip over x-axis, flip over y-axis, vertically stretch, vertically compress, horizontal stretch, horizontal compress. And yeah, those 10 transformations are very basic. I think my videos cover those 10 transformations. After I finish that in a class, I don't really feel like very efficient. Very important about transformations is we want to use the parent function. Transformations of what? Transformations of a parent function. So this section, we study the transformations. Study the transformations of what? Transformations of a parent function. And what is a parent function? Parent function normally refer to a very simple function. For example, a linear function, right? Or this is called a square function. Remember, I want you to get yourself familiar with those very important functions. This is a parabola, and the most simple parabola, y equals x squared. Other parabolas can be seen as transformations of this one. Okay, yeah, this would consider as the parent function of a parabola. It's called a square function. And what if the exponent is 3? Cubic function, right? And its inverse function is cube root function. You remember those functions from last activity? Reciprocal function, right? Square root function, okay? And what is this? Last activity, the three graphs on the top. Absolute value function. Absolute value function, okay? Yeah, those functions, you need to know their graphs, their characteristics very, very well. Okay? Yeah, you should write it down. Square function, square root function, cubic function, cube root function, reciprocal function, absolute value function. Those functions are so simple, so basic, they are considered as the parent function. And the transformations are going to be applied on those parent function. But firstly, you have to know what those parent function look like, right? Okay, for example, this problem. Let me erase those. When you rewatch the recording, I have the recording. I have the classes recorded right now. You can pause and then take notes. Parent function. Use only parent functions for this problem. The graph of G, which is a negative square root of x plus 1 plus 2, can be obtained from the graph of what? They ask you which function can be the parent function of this function G. What do you think?
Square root.
Yeah. Square root of x. Yeah, square root function. Knowing here, you are going to just enter square root of x, okay? You are not going to write the parent function is y equals root x. Oh, I know, y equals root x. No, okay, because they already have a y equal. I mentioned that earlier, right? This happened in previous semester. Oh, I struggled. Should I overwrite? But the students should have paid attention, right? You write root x. That's the parent function. Parent function, square root of x, okay? Do you know the graph of the square root function? You need to be very, very familiar with the graph of the parent function. In this case, is the square root function, okay? Firstly, when x equals 0, y is 0. When x equals 1, square root of 1 is 1. When x equals 2, square root of x is root 2. But root 2 is irrational, is around equal to 1.414, but it's not convenient, right? Then you would want to consider when x equals 4. When x equals 4, 1, 2, 3, 4, x, y, square root of 4 is equals 2, right? When x equals 9 is 3. So you can find as many points as you want, and you will see the parent function, square root function look like this. Okay? We can see this 0, 0 as the end point of the curve. And it does not have an end point on the other direction. It is extending to infinity. Okay? So this is the parent function. What's the domain of the parent function, everyone? What's the domain? What is the domain of the function?
X.
0 infinity?
Yeah, exactly. What's the range of the function? Vertical? You can try the rectangle method I taught. It is a good method. Range, go vertical. Do we have anything below 0 for y?
Or infinity as well.
Yeah, same thing. Very good, very good. As you can see, the curve only appears in quadrant 1, right? Yeah, at the origin of quadrant 1. Very good. So you need to be very familiar with everything about this parent function, okay? Okay, so now let's read the requirement. What do we need to do here next? By first reflecting the graph through then shifting the graph. Okay, so now we're going to look at the transformation. We start with the parent function. Yeah, how do we get there? This is the g of x is the final, is the I call daughter function. Okay, so firstly, yeah, this question is good because it reminds you. Firstly, reflect the graph through which axis? So we are going to flip the graph over x-axis. X-axis. What does that mean? Why? What is x-axis? Okay, let's see if we flip the graph over x-axis. The red curve is the parent function, right? If we flip it over x-axis, we would have this blue curve, correct? Blue curve?
Yeah.
Yeah. And that is graphically. If you flip the graph over x-axis, that's the mirror, right? X-axis is the mirror. Then you have the blue curve. But algebraically, the function you're gonna have, when you flip the function over x-axis, you change all the y values to their opposites. So you are going to multiply the whole function by -1. You're gonna multiply the whole function by -1. So you have a negative root x. The whole function is y, right? Whole function is root x. You are going to multiply whole function by -1 or attach a negative sign in front of the function. So you have a negative root x. Okay? The graph of negative root x is the blue curve. The graph of negative root x is y equals negative root x is y equals root x. Okay? Yeah. The good thing is this question guides you through And next step, this time we already have y equals negative x, the blue curve, okay? After the first transformation, we have negative x. After that, shift the graph, yeah, to get a what? So this time we are going to shift to the left 1 unit.
Because it's negative?
Shift to the left 1. Yeah, this is the confusing part, everybody. Shift to the left 1 unit. When you shift the graph horizontally, let's say move the graph, shift the graph horizontally to the left 1 unit, you end up with plus 1 to x.
What?
That is a little bit anti-intuitive, but this is the correct way.
Is
When
it
you
because
move,
the negative sign is on the outside of the square root? So you put the
no,
positive one?
no, I'm sorry, it has nothing to do with that. Has nothing to do with that. It is because in order for this function to reach the same output, yeah, after you shift to the left, in order for the y value remains the same, x have to be 1 unit left in order to have the same. So let's do this. Let's do this. This point is 1, 1. It is 0, 0, 1, 1, 4, 2, right? And this blue one here. And this 1, 1 becomes 1, negative 1, right? 4, 2 becomes 4, negative 2, right? Let me erase the domain and range, make it better. So 1, 1 becomes 1, negative 1. 4, 2 becomes 4, negative 2, right? All right. So now, if we move the blue curve to the left 1 unit, what color do we want? We want a green color. Okay. Then 0, 0. Yeah. So the blue, on the blue we have 0, 0, 1, negative 1. We have 4, negative 2. If we move all the 3 points, they are representatives, right? To the left 1 unit, their x values gonna be 1 unit less, right? So the 0, 0 gonna become negative 1, 0, right? Negative 1, 0. And this point is gonna shift to 0, negative 1. Yeah, every point is gonna be 1 unit left. This one is gonna be 3, negative 2, right? Yeah. So those points, the 3 points, gonna become negative 1, 0, 0, negative 1, 3, negative 2, right? Yeah, left, yeah, minus 1 from x. Minus 1 from x. Okay, and then we connect them. And the green curve is the square root of negative x plus 1. Okay, let's plug in. When x equals negative 1, yeah, plug in when x equals negative 1. What's y value? We are looking at the yellow function. Plugging in x equals negative 1, 0. Plugging x equals negative 1. Do you have a 0 as output?
Yes.
Yeah. But if you don't believe me, oh, you know, it's a plus 1, so it's supposed to be to the right, right? or if you have moved to the left 1, then it's supposed to be x minus 1. And you try again. You try again, those points will not satisfy the function. You see that? When x equals -1, you have -2. It's not even defined. Do you see what I'm talking about? It is a little bit anti-intuitive. You figured out when we move the curve to the left 1 unit, we end up add 1 plus 1 to x. If we move the function to the right 1 unit, we minus 1 from x. In my PowerPoint, I have a more detailed explanation about that. So now we have that. Let's keep going, because our g has a +2 there, right? Our g is almost there. Alex, does that make some sense now? Alex?
Sorta.
Sorta, okay. But you understand, if I change this to -1, those points will not work, right? Yeah, that means it has to be +1. Yeah, so our g is negative root x plus 1, the green curve, and then +2. So the 2 here is added to the green function, added to y. When you add a number to y, that's obviously up, okay? Up to means y value. What color I'm gonna do? Orange. That means y value add 2 to y. Okay, y value like increased by 2, right? So the -1, x remains the same, y value increased by 2, 0 plus 2. X remains the same. -1 plus 2 is a +1. 3, -2 plus 2 is 0, right? So all those green points gonna go up 2 units. 2, 1, 2, so it's here. And here. And here. So it's gonna look like that. It's gonna look like that. The orange curve. The orange curve, the final function g, gonna passing through -1, 2, 0, 1, 3, 0. All right? Using convenient points are so important in this section. Okay? So look at the given function, given graph. We're given 4 graphs. Which one passing through -1, 2? That's the end point, very important. And the shape is concave down, right? The shape is concave down. Since the concave down, concave up. Concave up, like smiling. So this is wrong because concave down. Has to be this one, right? You see that? This is 0, -1, 2. Yeah, this is -1, 2. And here we have 0, 1. We have 3, 0, 1, 2, 3. That definitely is a correct curve. You see that? Yes or no? I'm going to do it again here, okay? I'm gonna do it again. Let me get more space. How do you process this type of problem? Use a convenient point is very important. The daughter function is negative square root x plus 1 plus 2, okay? First, you need to know the parent function, mother function is x equals root x. As it's important to find some convenient point. The convenient point, what we have here for this parent function, 0, 0, because when x equals 0, y is 0. 1, 1, because when x equals 1, y is 1. 4 comma 2, because when x equals 4, square root of 4 is 2, right? I think 3 is enough. Okay. Firstly, we're gonna flip over x-axis. Okay, graphically, we mirror the graph over x-axis. Algebraically, we are going to attach a negative sign in front of the entire function. This is the y, guys. This is the original y. Change the y to the opposite, okay? So that change, we'll change here. We are going to change y value to their opposites. Okay, keep the x value. Keep 0, x value. Change y value to -0, is still 0. Keep x value, change y value to negative, to opposite. Keep x value, change y value to the opposite, right? Okay. Next step, we are going to, since we need a +1 here, right? Yeah. Since we need a negative, sorry, +1 here. That means shift to the right, to the left, to the left 1 unit. Yeah, very, very important. If you mess this up, you won't be able to get it right. Horizontal shift is a little bit counterintuitive. If we add a 1 to x, that means shift to the left 1 unit. Okay, that means what? What are those points gonna change? Those points shifted to the left 1 unit. That means their x gonna be 1 unit less. So we're going to minus 1 from x. Subtract 1 from x. Yeah, subtract 1 from x. Keep y. 0 minus 1, -1. Keep y. 1 minus 1, 0. Keep y. 4 minus 1, 3. Keep y, right? Okay. The last step, we add 2. We add 2 to the entire function, means we add 2 to y. That means we're gonna go up 2 units, right? Go up 2 units, what will happen to those points? Means the y value gonna go up by 2. That means we are going to add 2 to all the y values. X remains the same. X remains the same. Y value plus 2. 0 plus 2. X remains the same. Y value plus 2. -1 plus 2, +1. X value remains the same. Y value plus 2, -2 plus 2, 0. And with those 3 convenient points, you are able to choose the correct graph for this function. Is that clear, everyone?
I have a question. Okay, when we're shifting it along the x-axis, right?
Horizontal shift.
The shift, when we're adding the 1 to the x.
Yeah, horizontal shift. Yeah,
Yes.
left or right. Yeah.
Yes. We're adding the 1 to the x alone, but when we're changing it like vertically, we're adding the 2 to the entire
Function. Yeah, we're adding 2 to y.
to y.
Yeah, to y. This is the y.
Okay.
If you add 2 to y, that's a vertical shift. Yeah.
Okay. So in a case where we don't have the square root, like the radicand, I think.
The parent function?
Yes, the parent function is like just x squared, right? And we have to shift it along the horizontal line and then later shift it to the along the vertical line. How do you differentiate that this is just a shift to the x and this is a shift to the y? because it's just going to be x, right? So if you're adding like x plus 1 and then eventually it's x plus 2, like if you flip it, is there like okay, I think I'm getting lost in my train of thought. I don't know.
The context, the question
Yes.
would make it clear. I
Okay.
don't think you will get confused on that.
Okay.
But this is so important because you're gonna see something similar in the exam, guys. Am I making this question very clear? Maybe the question you see on the exam a little bit different. Maybe here is plus 3. Then you have to shift it to the left 3 units. Maybe here is going up 5 units. But the structure of the problem would be the same problem. Is that clear, everyone? Yeah, transformation is very, you know, this file, let me show you this file. Took me many hours. Is 1.6 transformation. But if you go through the file, you would learn, okay? Yeah, actually it's not that bad, just 10, not that bad. How many pages? Look at that. 66. It took me many hours. It took me many hours. But I have it very in detailed. Which hold on, this is 1 point transformation, yeah. Transformation, yeah, parent, yeah, I write mother function, daughter function. I show you how do we find the like this, yeah. This one is very similar with the problem we just went over, right? This one is very similar. Which is step. I would recommend you spend time to go through those. Yeah, shift right. When we shift right means we minus 4 from x. Yeah. When we shift to the right 4 units, graphically, algebraically, we minus 4 from x. Yeah, horizontal shift, we plus or minus the number from x. Horizontal, we change the number for x. Vertical, we change the number for y. If we add 3 to the entire function, we go up. That's very intuitive. If you go through those problems, I believe you would understand it eventually. Right? This is a transformation of the absolute value function. This is a vertical stretch by 2. Absolute value of x is the y. When you multiply the y value by 2, means you doubled the y values, right? You keep the x value, double the y value, find some convenient numbers. Yeah, use the method that I used earlier, like finding the convenient numbers that would help you to graph it. The daughter function normally have the same shape with the parent function. And if you know a few points on the daughter function, then you should be able to graph it very easily. Okay? Yeah, this is, yeah, how do we get that done? Yeah. Double, stretch vertically by 2, shift, since here's the plus 1 to x, so shift to the left 1. Since here's the minus 2 from the entire function, we go down by 2. And pick 5 points on the parent function. And correspondingly, those 5 points would change, right? And that means those 5 points be on the daughter function. And use those 5 points, you would be able to draw the graph of the daughter function. Yeah, they are very similar. You just need to practice. Similar with this one. You have those convenient points on the mother function, right? After those transformation, those 5 points would become those 5 points. And you're going to use those points to draw the daughter function. This one, vertically compress. Y value is shrunk to the half of the original. So yeah, vertically compress by 2. will reduce to the half of the original, right? And then since here is plus 2 to x, as you can see, I'm pointing it, plus 2 to x, that means shift to the left. Here, you minus 2 to the entire function, from the entire function. That means vertically down 2 units. And you're gonna have to look at those and get yourself familiar with those questions. I think it would be fine. And let's practice more. Let me look at the time. Yeah, let's practice more about transformation. Yeah, this one is a good one. This question gives -1 from the y, -1 from x, +1 from y, +1 to y, +1 to x. Yeah, either have all the 4 shifting, 2 horizontal shift and vertical shifts. Let's see how do we do that. Let's see what happened to h. What happened to f to get h? This is the f. This is h. Yeah, what happened? As we can see, the x value remains the same, right? X value remains the same. That means x value doesn't change. That means horizontally, no shift. Horizontally, no shift. Vertical y value changed from -2 to -1. -2 plus 1 gives plus -1, right? -2 plus 1. -2 plus 1 gives -1. 4 plus 1 gives 5. 4 plus 1 gives 5. 3 plus 1 gives 4. -1 plus 1 gives 0. 2 plus 1 gives 3. So obviously, no horizontal shift. No horizontal shift. There is a vertical shift. Yeah, since all the y value increased by 1, shift upward by 1. Okay, up 1. Up 1. Up 1 means you're gonna add 1 to the entire function. Add 1 to y. What is y? Y is f of x. Does that make any sense, everyone? Does that make any sense, everyone?
Yeah.
It does.
Okay. Okay. And this one, yeah, this is also a good problem because this one involves flip over x-axis and then flip over y-axis. It's very interesting. We know the mother function, right? Yeah, we have been talking about the mother function, the square root function a lot today. It looks like this. It passes through 0, 0, 1, 1, 4, 2, right? And this problem asks us to yeah, this is the mother function. It's given 0, 0, 1, 1, 4, 2. Yeah. And this one asks us to write the transformation of the parent function, to write g and h as transformation of f. And this one obviously passing through 0, 0. So I'm gonna write this down. 1, 1, 4, 2. And then for g, we have 0, 0. We have a 1, -1. We have a 4, -2. Just look at the points. Just look at the points. X value remains the same, right? 0, 1, 4. But y values become their opposites. 0 becomes 0, -0. 1 becomes -1. 2 become -2, right? That when you have to change all the y values of a function to their opposites. You flipped over x-axis. You flipped over x-axis, right? You flip over x-axis. So the function is going to be, so change all the y value to negative. And what is y? Y is root x. So your function is y equals negative root x. So how do we enter it? You are going to enter g of x equals negative root x, because you are changing y value to their opposites, okay? For h, let's see what happened to h. 0, 0, negative 1, 1, negative 4, 2. We're comparing h with f. Ignore g. We're comparing h with f. For f, we have a 0, 0, 1, 1, 4, 2. For h, we have a 0, 0, negative 1, 1, negative 4, 2. So y value doesn't change. Y value does not change. X value become their opposite. X value becomes opposite. That means you change all the x to negative x, right? So your h of x is root negative x, okay? So if you flip a graph over x-axis, you attach a negative sign to y, put a negative sign in front of y, in front of the function. When you flip the function over y-axis, you attach the negative sign in front of x. And let me know if it's clear.
Makes sense.
Okay, thank you. All right, we want to talk about the rest of the time. We want to talk about even function, odd function, this topic, okay? On my PowerPoint, I also give that very detailed definition. Okay, even function. Let's say y equals f of x is a function, and the domain is D, okay? If it satisfies the following two conditions, then the function is an even function, okay? What is even function? The first condition, the domain is symmetric with respect to the origin 0, okay? And the domain has to be symmetric. This is the origin. Domain is on the x-axis, right? Yeah, the domain is symmetric. Maybe from negative 5 to 5, right? Or maybe from negative infinity to infinity, that is symmetric. If you have the function domain is 0 to infinity, you don't have to look at the second condition. That function is neither odd or even. It's neither. Because for an even or odd function, the domain has to be symmetric with respect to the origin. Okay, a lot of people, even the book, doesn't emphasize that, which is wrong. It is important, okay? It's important. If the domain of the function is not symmetric with respect to 0, we don't even have to consider if it's even or odd. It's neither, okay? If that is satisfied, and for any x in the domain, f of negative x equals f of x, then if f of x satisfies both conditions, f of x is an even function. Yeah, this is the condition. F of negative x equals f of x. That means if you flip, let me give you an example. Y equals x squared. This is a square function. All right. If you flip this function over y-axis, do you have the same thing? Do you have the same thing?
Yes, your y value remains the same.
Yeah, y value remains the same. Yeah, if you y value remains the same, and if you flip this graph over y-axis, and this arm gonna go to the left, this arm gonna go to the right, but the graph gonna look the same, right? Then the function is even. Yeah. So graphically, an even function is symmetric. The graph is symmetric with respect to the y-axis. Graph symmetric with respect to y-axis. All right. Yeah. Let me summarize. Even. For a function to be even, firstly, domain has to be symmetric with respect to 0. On top of that, f of a negative x has to be the same with f of x. Graphically, if a function is even, its graph is symmetric with respect to the y-axis. Okay, that's even. What about odd? Let's say we have function f of x, domain is D. If the function satisfies the following two conditions, first condition D, domain is symmetric with respect to the origin. And for all the x, f of negative x equals negative f of x. It's different, right? F of negative x equals negative f of x. Then the function f is odd. You can understand this condition as f of negative x plus f of x equals 0, if that helps you to remember. Same thing. Graphically, an odd function, the graph, if a function is odd, the graph is symmetric with respect to the origin, 0. I'll explain what is respect to origin means, okay? A very simple odd function is y equals cube, the cubic function. Yeah, I'm gonna mention those very important function, basic functions a lot. Yeah, you're gonna be very familiar with the graph of those functions. So what's the graph of cubic function? It looks like this. This function is odd. It is the graph is symmetric with respect to the origin. What does that mean? Means if we rotate the graph, doesn't matter counterclockwise or clockwise, 180 degree, the graph overlap itself. Will go back, right? Just imagine this arm gonna become this arm, and this arm is gonna become this arm. Yeah. So if you rotate this curve, of course, with respect to the origin, like 180 degree, and the graph become the original graph. If a function whose graph is symmetric with respect to the origin, that function is odd. Algebraically, the condition is f of x and f of negative x add up to 0, okay? So remember those important things, and now we can look at this problem. Yeah, this is gonna be on the exam as well, so make sure that you pay really attention. Let's see, how do I find a space for that? Find a space for that, okay. Paste, oh no. this one. Copy. All right, so what? Hold on. For each equation below, determine if the function odd, even, or neither, right? Okay, I'm gonna just write them down. First function, absolute value of x plus 4. Okay. First function, f of x equals absolute value of x plus 4. Okay. Our requirement, our goal here is to determine if the function even, odd, or neither, right? Yeah, that's the goal. That's the purpose. Okay. And this is the function. And you're gonna go ahead to find f of negative x. Technically, we should look at the domain first, right? Are you able to determine the domain? Remember in the activity last week, you see this graph. I draw this graph. This graph is the graph of the absolute value function. Absolute value function is also very important. It's very interesting, right? This is 1, 1, negative 1, 1. Yeah. So obviously the domains are real, is symmetric with respect to the origin. And you're going to go ahead to find f of negative x. Change x with negative x. Yeah. Keep everything the same, only replace x with negative x. What's the absolute value of negative x? Isn't that the same? Isn't the absolute value of the opposite of x same with the absolute value of x? You know what I'm saying? Because let's think about what's absolute value of 5? What's absolute value of negative 5? What's absolute value of 7? Negative 7? Yeah, you can find as many numbers you want until you feel comfortable. Negative 10. Absolute value of numbers is defined as the distance between the number and the origin. Okay? Absolute value of 5 is 5, 7, 10. I believe you know that. Absolute value of negative 5 is also positive 5. Because the distance between negative 5 and 0 is also 5. 7 is 10. Do you agree, guys?
Yes, it makes sense.
Okay, thank you for your
So
response.
it'll be even
Yes.
with a vertical shift of 4.
Yes. Oh, is even. And this has nothing to do with the transformation. Yeah. Yeah, you're right. You mentioned that. 1, 2, 3. Yeah. So this is the parent function. So our function is like this. You know? Yeah. It's also even. It's gonna be 4 units above this radar curve. Yeah. This is the transformation. You're right. This is the transformation of the parent function. The parent function is even, and the transformation only have a shift vertical transformation, so it doesn't change the even function feature. So still even. Yeah. Very good. Second question. Second problem, 1 over x plus 4x. 1 over x. 1 over x plus 4x, right? Okay. So let's look at the domain. What's the domain, everybody? Is that all real or not? Is all real except 0 because we have a denominator, right? X is in the denominator, so x cannot be 0. Yeah, all real except 0 is also symmetric with respect to the origin. Yeah, even sometimes you would say, I never look at the domain, but I can answer my question correctly. That is okay, because they don't require very strictly on this. But technically, we should always check the domain. But it's good to know, right? Also good to know. And we're going to go ahead to find a g of negative x. It's going to be negative 1 over x minus 4x. Compare with g of x, you notice is negative g of x. Or if you add g of x and then g of negative x, you'll see that you have a 0. Okay? About this part, I want to mention a formula. Yeah, I need to remember to include that in the formula book. Negative a or b for a fraction. The negative sign can be placed with the numerator or the denominator. All the three expressions are the same. Yeah, the negative sign can stay with the denominator or the numerator or in front of the quotient. So that's why 1 over negative x can be written as negative 1 over x. All right? So tell me, even or odd?
It'll be odd.
Since you are allowed to have a graphing calculator, if you really don't know how to do this, you can, if you don't know how to do the algebraic method, you can use the graphing method. Simply graph the function to see if it is symmetric with respect to y-axis. If yes, it's even. If you graph the function, you see the function is symmetric with respect to the origin. That's odd, right? If neither is neither, yeah. But algebraically determine even or odd is important. Let's see number 3. X squared plus 4x. X squared plus 4x. H of x. Domains are real. No restriction on x, right? And let's look at the h of negative x. That is negative x to the power 2 plus 4 times negative x, which is x squared minus 4x. Just look at h of x is x squared plus 4x. H of negative x is x squared minus 4x. They are not the same. So they are not, the function is not even. They do not add up to 0. They do not add up to 0. They would add up to twice of x squared. So it's not odd either. So this is neither. Is that clear, everyone?
Yeah.
Yeah. So even, odd, yeah, it's not very difficult to grasp. Just know the basics. And I hope you don't miss this problem on the exam. Yeah, this will be on the exam. Okay. Do you guys have any questions? I would really strongly recommend you look at the PowerPoint I made. I spent a lot of time on it, and you figured out my solutions, and you would learn how to do it yourself. And also pay very attention. Take those questions we covered today very seriously because they are going to be on the exam. Maybe the number would change a little bit. Maybe this is a +3, right? Maybe this one is a +5x, but the structure is the same thing. Okay, guys. 10, including me, so 9. We have 12 students, so we're missing 3. Who are we missing? The last few minutes, we are going to take attendance. And then we'll be done, okay?
Sounds good.
Mm-hmm. This is
That's
2 days.
Monday's meeting.
Yeah, I'm gonna delete this one. Today. Save. And another section, this one. This is Monday. Delete this meeting. And this one today. Jonathan is excused. His power went out. Excused. Who else I'm missing? JC? Is JC here? JC's not here. Cameron Drew. is here. Jose is here. Alex is here. Stephanie is here. Paula is here. Camila is here. Cameron S
I'm here.
is here. Yeah. Angelina is here. Madison. Is Madison here? No. Okay. And save. All right. I'll do the same thing for the essential. That's everything for today. Everyone, if you have any questions, please feel free to reach out. I hope to see you on Monday for sure, probably. There's no reason we don't meet on Monday, right? Essential today. Jonathan accused. Medicine absent. Save. Okay, all done today. I'll see you on Monday, everybody. Have a good weekend.
Awesome. Thank you.
You too.
You're
See you
welcome.
Monday. Have a nice day.
You have a
Thank
good
you
one.
too. Thank you, Paula. Bye-bye.